So, in this whole chapter 5, we've been talking about ideal gases. However, in reality, ideal gases don't exist. Real gases are not ideal gases. And let's just take a look at what ideal gases are again. PV equals nRT. Ideal gases do not attract between gas molecules, they're ghosts to each other, and they don't take up space. And in reality, none of this holds true for gases. It's a good assumption though. So let's look at ideal gas molar volume. And if you look at 6 different gases, they're all roughly right around 22.41. So it's a very good assumption that they do interact like ideal gases. We just have to be aware that real gases are not ideal. Because real gases do have size. At low pressure, their size doesn't matter, but at high pressure, it really does. And that can be shown here. So we have 2 cylinders. At low pressure, the gas molecules are really far from each other, and so they don't interact with each other. However, at high pressure, the gas molecules are very close to each other, so they're going to start hitting each other. And so at high pressures, extremely high pressures, look, we're talking about 400, 600, 800 atmospheres, the molar volume of argon and ideal gas are different because you're actually pressing against the gas molecules at this high of a pressure, and so you're starting to get resistance from gas molecules because they do have size. Unlike here in the ideal gas, they don't have size, so you can keep pressing and pressing and pressing further. Now, at high pressures, the ideal gas law predicts a smaller volume, like we just said, because it doesn't account for gas taking up volume. But there was a scientist, his last name is van der Waals. He made a correction to the ideal gas law to take this into consideration, where he said volume equals nRT divided by P, and that's the ideal gas law, plus this correction factor, where N is number of moles, and B is just some constant that depends on the type of gas. And this NB term, this accounts for intermolecular forces. And intermolecular forces, you'll learn about it in Gen Chem 2, but it's just attraction between atoms and molecules. In gases, normally, there are no forces. They don't really feel each other. Because at low pressure or at high temperature, they're either too spread out or moving too fast to feel each other. But if you're at low temperature, gas moves very slow. So if you are moving very slow, when you hit each other, you're likely that you're going to stick together. And that's where these intermolecular forces matter. And when you stick together, you're going to have an effect on pressure and volume. And so they stick together, these gas molecules. Therefore, they're going to collide into other things left often. So real gases at low temperatures have lower pressures than what the ideal gas law actually predicts. And that's what's shown here. So we have a temperature going close to 0 degrees, and here's xenon. You can see at high temperatures, ideal gas and xenon are roughly the same. But even at room temperature, 298, there's quite a big difference on what the ideal pressure is. And so we have a constant term to help with that, where A is just a constant that depends on the gas, multiplied by N divided by V, moles divided by volume squared. So we just have to reduce the amount of pressure we have because it is lower. And we can combine these two equations and we get unified van der Waals equation, where we're saying we have to correct for intermolecular forces and we have to correct for volume. And when we do that, we can start to see gases, we can start to predict gases behaving like they really do. Now, we're not going to do calculations using this, but I just want you to be aware that real gases are different than ideal gases. The reasons are because ideal gases do have volume, real gases do have intermolecular forces, and we can make corrections to the ideal gas law to account for these. Alright, that's your last video on Chapter 5, so I'll see you in Chapter 6.